Hey everybody, we're back with our finishing touches on our video on velocity and other rates of change. So we're going to finish up here with example 2 so that you're able to do your mastery with this lesson. So I'm going to read you this problem. It says, a ball is dropped from the top of the Empire State Building, which is 1,002 feet above the ground. The ball's position is given by the equation, so let me highlight this. S of t equals 16t squared, where t is measured in seconds and s is measured in feet. So this equation right here is going to give us the ball's position at any time t. Okay, but we got to think a little bit differently here, because when I first did this problem, I was kind of confused. I'm used to finding the position of like something that starts on the ground and gets thrown upward. When I say you're going to be able to find the position here, this is basically going to give you the position from 1,002 feet above the ground. So for example, if I plug 1 second into this equation, S of 1 is going to be 16. So that means that at 1 second, I'm not at 16 feet, I'm at 1,002 minus 16 feet, so I'm at 986 feet. So hopefully that makes sense. It's a little bit different because we're starting in the air. Okay, so the first question says, what is the average velocity of the ball for the first 2 seconds? Now, average velocity is not, I repeat, not instantaneous velocity. So I'm not taking a derivative. I don't want the slope of a tangent line here. I just kind of want a general slope on the first 2 seconds. So I'm going to go back to that formula we did on the last video. Where is it? Right here. So average velocity, right here. Position at ending time minus position at start divided by the elapsed time. So when I set this up, it's going to be average velocity on, I like to say, the time interval 0 to 2 seconds. That's the first 2 seconds. So the average velocity on the first 2 seconds is the position at the ending time, which is 2 seconds, minus the position at the start, which is 0 seconds, divided by the elapsed time, which is 2 seconds minus 0 seconds. Okay, so now I'm going to plug in. So the position at 2 seconds. Now, got to be clever here. Let's plug 2 in. So if I take 16 times 2 squared. Okay, this means 64 feet, but that's not my position. My position is actually 1,002 minus 64 feet because I've traveled 64 feet downward. So I'm really at 938 feet off the ground. That's my position from the top of the Empire State Building after 2 seconds. Okay, well, my position at 0 seconds was the top of this building, 1,002. Over 2 minus 0 is 2 seconds. So I have a change in position of how much? Let's see. I go 938 minus 1,002. That means I dropped 64 feet. So I dropped 64 feet in 2 seconds. Therefore, my average velocity on that first 2 seconds was negative 32 feet each second. Boom. That's my average velocity. Okay. Next, how long does it take for the ball to hit the ground? So how long does it take for the ball to have traveled 1,002 feet? So when was the position basically 1,002 feet? So I'm going to set 16t squared equal to 1,002, and that'll give me the time when I've traveled 1,002 feet. So I'm going to divide both sides by 16. So t squared equals, what is that? 1,002 divided by 16 is 62.625. And then I'll square root both sides. So t is approximately the square root of 62.625, 7.914 seconds. And you can see, if you plug that into position, if I take 16 times, what was that, 7.914 squared, see, I get 1,002 feet. So yes, it took that long for me to hit the ground. All right, almost done. What is the average velocity of the ball during the whole time it's falling? So not just the first 2 seconds, but all 7.914 seconds of the fall. So now that's going to look like this. Average velocity on the time interval 0 to 7.914 seconds equals the position at 7.914 seconds minus the position at 0 all over 7.914 minus 0. So the change in position divided by the change in time. Well, my position at 7.914 seconds was that I was on the ground. So I'm going to say 0 feet minus the position at starting time was 1,002 feet. I was at the top of the building, all over 7.914. And if I take negative 1,002 divided by 7.914, I get negative 126.611 feet per second. So that means I was going downward, that's the negative. My ball was falling down at an average speed of 126.611 feet per second. And that's over the entire length of time the ball was falling. That's the average. And last but not least, what is the velocity of the ball when it hits the ground? So what is the velocity when the time is 7.914 seconds? Because that's the time when the ball hit the ground. Okay, now I do want instantaneous velocity. How fast was the ball going at the instant it hit the ground? This is derivative. So if position is 16t squared, then velocity is the derivative of that, which is 32t, power rule, and the velocity at 7.914 seconds is 32 times 7.914 seconds, which is going to give me 7.914, 253.248. 253.248 feet per second. That's how quickly we were moving. And I just thought of something. To be honest with you guys, I should not have rounded. For example, like when I'm putting 7.914 in here, see, that was a rounded value. I should really be using the entire decimal or keep putting it in as the square root of 62.625, because watch the difference. If I take 32 times the square root of 62.625, look at the difference here. See, I get 253.235 feet per second. And that is different than this. Here I had 248. The unrounded version is 235. So I should have done that. So how would that change up here? Actually, it won't change. Well, yes, it will change this. So instead of dividing by 7.914 here on part C, I should have done 1,002 divided by the square root of 62.625. Still 126, but now it's 618, not 611. So just trying to be as accurate as possible. Okay, so that's it. Now you are ready to do your mastery. So your mastery is these 4 problems. So good luck with those. Number 3 is multiple choice, but numbers 1, 2, and 4 have different parts to them, kind of like this had different parts. All right, good luck and thanks for watching.